All right. In the interest of time, we'll get started as people are trickling in. Good afternoon, everyone, and welcome to our webinar today. I'm Madhu Khanna, Professor of Environmental Economics and the Interim Director at the Institute for Sustainability, Energy, and Environment at the University of Illinois, Urbana-Champaign. The webinar today is part of the Fall Congress that is organized by the Institute, and this year's theme is Circular Food Systems. Making our agricultural and food system circular so that it reduces, reuses, and recycles waste while continuing to increase productivity and economic well-being is a major challenge for the coming decades for the agriculture and food sector. And it's going to be made even more challenging with a changing climate system. This is a challenge that requires combining knowledge from different disciplinary perspectives and the need for holistic solutions that harness new technologies, market-based incentives, and policies. I'm delighted that we have 4 leading thinkers as our panelists today. They will present their perspectives on what it means to have a circular economy in food and agriculture and strategies for achieving this transformation. Before I introduce our speakers today, I want to briefly thank the organizations who are helping to co-host, co-sponsor, and endorse this session. We are thrilled to have the Council on Food, Agriculture, and Resource Economics as a co-sponsor and a co-host of this event. Seafair's mission is to translate knowledge generated by agricultural and applied economics professionals into educational programming. Additionally, we're delighted this event received endorsement from the Agricultural and Applied Economics Association and the American Society of Agricultural and Biological Engineers. And we're really glad that we have members of both organizations in attendance today. The webinar today is the second of 4 webinars that is being hosted by the Institute for Sustainability at the University of Illinois on this topic. The Institute has a 3-part mission of fostering actionable interdisciplinary research, education, and outreach to address global grand challenges related to sustainability and to lead efforts to make our university campus carbon neutral in the coming decades. Our annual Congress is being held virtually this year in the form of webinars, and we will provide information about the 2 remaining webinars that we are hosting in November on this topic at the end of the session today. We're hoping this will be an interactive discussion today with our 4 speakers. We will hold questions till after they have completed their remarks. Please feel free to post your question as they occur in the Zoom Q&A, and we will take time after our speakers have finished their talks to address as many as we can. And now it is my pleasure to introduce our 4 speakers who are going to discuss how we can transform food systems for a circular economy. We're going to change the order a little bit, and we're going to start with Dr. Jones as our first speaker. Dr. Jim Jones is a distinguished professor emeritus of agricultural systems modeling at the University of Florida. He currently serves on the National Academy Board on Agriculture and Natural Resources in the National Academy of Sciences. His work emphasizes use of convergent system approaches to develop food and agricultural systems that are more productive, sustainable, and resilient. His presentation is titled Transforming Food and Agricultural Systems Guided by Circular Economy Concepts. So Jim, I'll let you start.
Thank you, Mata. I appreciate this opportunity that you've given me today to be in this distinguished series. And I'm going to start out, next slide, please. I'm going to start out just talking just a brief bit about our food and agricultural systems, but they're really impressive. And I think all of us know that. They use advanced technologies, supply safe and affordable products to meet all of our needs, and we take them for granted as we go into the grocery stores and retail outlets to buy products that are produced in food and agricultural systems. And increasingly, we know how these different food and agricultural systems are interconnected with all other human and natural activities, creating complex nexus of food, energy, water, environment, health, and other systems. Various National Academy studies have concluded that current systems are inadequate to meet future demands. And Madhu pointed out some of these as well. I think all of us are aware of the challenges, and Madhu pointed those out. And so what I wanted to point out is that advancing our systems to increase productivity and profitability will not achieve the desired outcomes to increase the food supply and sustain natural resources and ecosystem health. So here I'm going to focus on circular economy concepts that help unify these different activities. And next slide. So there are many definitions of circular economies. And the one that I like to use is fairly simple. It's a systematic approach to economic development that benefits businesses, society, and the environment. But probably more importantly, in terms of guidelines for transforming, are the principles that have been defined by Ellen MacArthur and other groups. The first one is to design out waste and pollution, keep products and materials in use, regenerate natural systems such as soil and water, and also to provide economic benefits. And we've had several studies in the ASABE, American Society of Agricultural and Biological Engineers, that studied different types of supply chains for agriculture and food products. And we've identified a number of different key inputs and material cycles and outputs that are important, both for the provision of the desired supplies, but also the outputs that are causing externalities in the environment. Next slide. And so a part of that is we created a number of things that should be considered when we start trying to transform any particular system. And we have to remember that these are systems of systems. And the supply chain system scale includes pre-production, production, processing, packaging, and all of these subsystems that are interconnected to provide the products that we purchase. But there are also other scales that are important. I remember one of the first things that Chuck Ross asked me when we started talking about this earlier in Banner, well, at what scale? And there are many different scales. And that's one of the things I want to point out today, the importance of cross scale and also interconnectedness of the different components. In this, we found that it was important to identify the losses, inefficiencies, and waste in order to consider innovations that might help design out waste and contamination. And then we have to envision solutions that would contribute to more circular, sustainable, and resilient systems. And then create a roadmap, realizing that none of these are going to take place immediately. Next slide. This is a slide of a life cycle assessment, and I also point out digital twin models here as well. This slide was provided by Callie Babbitt, who made a presentation at the National Academy Forum last month on food and agricultural systems. And this shows all the different parts that are connected together to provide the products, and then there's waste that occur and losses that occur as well. This wasn't specific to food and agricultural systems, but there's a paper by Gustafson and others in 2021 in Nature Food that demonstrates the importance of these concepts in food and agricultural systems. Next slide. Oh, and yeah, just a comment on the previous one again. Those of us involved in engineering and agronomy and soil science and crop science and others, I mean, we typically work at these scales, at some subsystem or the entire chain, looking at how to better supply these. In that ASABE study, Bruno Basso led a study that he'll probably talk about more later that showed for corn soybean systems the ideas that we came up with when we were studying this. I mean, things that can be done now, as well as things that are anticipated in the next 5 or 10 years, and then longer term things that need to be put into place later on. So as a roadmap for really transitioning into these more circular and sustainable systems. Next slide. I did want to point out though, and this is a slide from Tom Hertl, who made a presentation at the National Academy of Engineering Forum last month also, that, you know, while we focus mostly on supply chains and supply, demand is critically important also. And this is where some of the other disciplines like economists and policy makers and so forth come in to deal with systems at different scales. And in Tom's paper, he pointed out that there are interdependencies across scales that can affect the trade-offs and the sustainability of the systems involved. And he pointed out here that he gave an example of the increasing biofuels in the Midwest by increasing corn production. And these local responses can have economic feedbacks to regional and global scales, and yet the global and regional scales can also have impacts to the outcomes there. Next slide. And then this is one of the results that he had. And if Tom were giving this, he could give you a lot more details, but in particular, he pointed out that the cross-scale analysis was really important because local responses are heterogeneous and they must be modeled locally. And that's another thing that we're doing in the food chains, I mean, in agricultural systems. We have models now that can be connected with economic models. We have models of cropping systems and livestock systems and soils and other things that can look into the future and imagine what new interventions might cause in transforming these systems, and then connect those to the scales of analysis that are done, such as the one that Tom presented here. Next slide. Pointed out that ASAB is doing some things internally and looking at a structure that will keep this going for the longer term. And we've been interacting with Madhu and AAEA, as well as Institute of Food Technologies, Tri-Societies, some different engineering professional societies and so forth. And there's strong interest by those who are working at the scale of providing operations and technologies that will supply food systems. And then National Academies, Chuck will probably talk about Banner's efforts, but the National Academy of Engineering also just had a forum on this and are highly interested in helping to engage other engineering disciplines more deeply than they've done in the past on helping us make some of these transformations. Next slide. This is the last slide, and I mainly wanted to point out a few things here that these we need holistic systems approaches for addressing supply chains, which is the scales that many of us work at, but also other scales in these hierarchical food and agricultural systems. We need convergence among engineering, science, industry, farmers, and society to address these complex systems. And some transformations may be disruptive. One of the leaders and developers of the Upside Food company that produces cellular meat also gave a talk in the National Academy of Engineering meeting last week. And these can be disruptive, whether or not they'll work, but we still have to take these into account and consider them. Two of the people also pointed out that we needed to have we need to have interdisciplinary education experiences at our universities and also continuing education for rethinking and redesigning these systems. And then that policies are also needed. So those are my comments, Madhu. I'll wait for questions maybe for other comments. And thank you again.
Yeah. I'd like to now introduce Dr. Bruno Basso. Dr. Basso is the Michigan State University Foundation Professor of Crop Modeling and Land Use Sustainability at Michigan State University. His research expertise is in crop modeling and land use sustainability. His presentation is titled Transforming Subsystems into Nature-Inspired Components for Circular Economies. Bruno?
Great. Thank you very much, Madhu. It's truly a pleasure for me to be able to share with you some of these thoughts and recent work that I've been doing with my lab on converting linear system into more sustainable and circular system. We all have a common goal, and almost independently of the type of discipline and research that we do, we're trying to basically converge towards this one health concept, trying to build, environment, food, and people's health. And they are very much interconnected, and a healthy environment leads to healthy foods and healthy minds and communities. And we are moving into a direction where it's not just the goal of, becoming sustainable, but also to invert the trend and be able to moving from a source of emission to a sink, and that's through regenerative agriculture as a very broad term, where we try to bring not just the science works with social scientists together to be able to again bring the socio-ecological resilience. As Jim has really clearly pointed out, when we talk about circular system, the first step is to define the system and quantify the interaction. So this is a very simple flow chart of, in the case of the subsystem that I'm dealing with today, is the corn and soybean wheat system across the US, mainly obviously concentrated in the 140 million hectares or so of land across the Midwest and the Lakes states and East and so on, where all the different inputs come in and the cycles are quantified. In my discipline, and through the possibility of being able to capture the interaction through a system approach, I have further basically divided each of this compartment. Like, for example, in the case of soil, we have to assess what are the variables that we can't just do very much about it. I mean, agriculture and soils, the soils is a leaky system. It just will never, we can never have zero leaching. There will always be some losses. And so the key point, especially in the context of, economics, is quantifying trade-offs. Where is the point? Where are the tipping points that if I do any extra action will not lead to any benefits, actually the system would collapse. And so just briefly, in nitrogen you want to reduce and the loss to the environment, emissions and leaching, but we want to improve in a very general sense, not in an economic, but you want to increase, nitrogen uptake. And so each of these compartments in the soil, in the plants, can be basically manipulated and quantified, at least with the interaction. And system approach through modeling plays a critical role and goes including water and energy. And so talking about trade-off has been something that has always been in my mind, in a sense that a farmer that makes a decision on how much fertilizer is applied by, again, working in these fields are very heterogeneous. And so the amount of fertilizer that you place in one area will have a different fate compared to what you do in another area. And so this is an example, the numbers, this is a study that I published about 10 years ago, where each of those numbers, 30, 60, 90, are the kilograms of nitrogen fertilizer that keep improving and getting net revenue, including the fixed the cost, just a simple calculation. But if we put more, then you reach a point that you would slightly increase. If you go from 90 to 120, the slope is still slightly on the positive, it may not justify the increase in leaching. But if you look at the low yielding areas of the field, then, the farmer will break even if it just puts, more 0, 30, more than 30, you lose money as well as environmental impact. And you can see the alternative in the medium zones, where if you put more than 60, you just don't make any money and increase environmental impact. So another way of doing it, converting that simple graphic as part of the initiative that Jim led within the Asabe, it's how we move from, this is just a simple example of changing fertilizer. What else changes? And so you have the units going in the soil and the residues being returned, how much is moved to the system. But again, this is still farm to gate. And so you can quantify the benefits of becoming more circular. And again, it's the example of fertilizer. But if we want to move, a little bit further, there is quite a bit more to explore. And the focus really of the next few slides are, how is technology going to help us moving into the direction of more sustainability? And these are a very, I guess, well-known, concept of yield mapping, be able to quantify yield variation over space and time at high resolution. And it's one of the example along what you see on top, the robots actually developed at the University of Illinois, and or the very high precision, be able to irrigate every single plant differently, or spraying differently, or quantifying thermal stresses and so on. So this variation are very large, and for a farmer to make a decision based on this flip-flop is very complicated. The problem is that if you use a uniform management, your inefficiency, it becomes very clear. You overestimate in some areas and underestimate in others. And this is a very well-adopted technology. About 68% of the US corn is harvested with yield monitor, and 45% of these areas is available to the yield map. But we took it a step forward in how we're going to analyze this spatial and temporal variation into how each single pixel varies from the neighbor and how it varies over space and time, to quantify how stable these conditions are. And so we were pleasantly surprised to see that there are areas that do not change in their direction. They're healthy and high performing, but problem, there are areas that they are constantly underperforming, and there are areas that they fluctuate from one year to the next. So by integrating, I wanted to be independent from yield mapping from farmers. And so I built a technology that scales using remotely sensed imagery and looking at the same place, the same pixel before the signal saturates. So it's explained in this paper, but now this is not a projection. This is every single field in this 80 million acres, where you can click on any single field and be able to get the stability maps. And so quantifying that in this particular example, the stable high yields are in 49 versus 32 of unstable and 19% of low productivity. And so by doing this analysis and pushing a little bit forward into the impacts, but before the impacts, we learned, which are very consistent across states, that about 50%, 48% of the areas are high productivity, with nitrogen use efficiency, in the case of this example with fertilizer, 75% use efficiency. But the problem is that 25% of these low productivity areas have less than 50%, 45% inefficiency, leading to, so basically learn the story that even here, the 20 to 80% rule works. 20% of the area produces 80% of the pollution. And so the impacts, you have 1.4 teragrams of nitrogen in the Mississippi, and this is the amount of money, 700 million on average, that only from the fertilizer I use, without calculating the additional cost later, and then the energy emission lost from the fertilizer as well as the CO2. And we also have a knowledge now on every single field. What are the fields prone, vulnerability to be water deficit or water access, in order to have a better, possibility to prescribe a variable rate and start becoming circular in that direction. So the analysis, please don't forgive me from talking about economics to a group of economists, but this is, we had very high. We basically have the income. We just don't have the bank accounts of the farmers that we collaborate with, which is a very large number. And so we used this is a true assessment of the expenses. And we did an analysis calculating a profit stability. So converting that in the bottom layer here, map on the right, 7 years of corn, these farmers could lose up to $200 an acre versus areas in the green where they make, more profit. And we know exactly where the low productivity areas are. So it's opening a new world of possibilities of scenarios. And for example, the areas that we quantify are 23 million acres of low productivity, and 15.5 million acres are in the field, but they're greater than 1 acre. So we're not talking about a Swiss cheese or doing zigzag. These are large areas that we have. There are more areas that they're smaller and they're not quantified here. But 7.5 million acres are on the edge of the field, which will allow quite a bit of logistics to be implemented. And so there are significant savings in nitrate leaching, all the way to pulling down 5 parts per million of CO2 per year, and carbon sequestration with a significant amount of biodiversity associated benefits. And so this is the beginning of converting this initial concept of precision conservation to more of a reality, where possibly, to me, again, precision conservation really starts by choosing the right piece of land and be able to allocate alternative land use that does not emit, is incentivized. So trade-offs and incentives and policy are critical in this in this conversation. And so farmers now could benefit by being incentivized to allocate within field CRP sorts of things, like low productivity areas, with a greater benefits of pulling CO2, perennials, no cost of seeds, no fertilizer, so no emission. We are quantifying to have a significant amount of greenhouse gas emissions reduction and carbon sequestration, as you've seen, but making profit and push the envelope in areas where you have a return. And so you got profit from the areas of greater yields and from incentivized. We also did an analysis of what if we were to convert, and this is work done within the GLBRC, and we work actually with Madhu on similar aspect of bioenergy on marginal land. And so the positive thing is that this land will start accumulating carbon while producing potential benefits. The market is not there yet, but all this evidence could potentially, with incentives, could change a little bit the game. And because of the knowledge, I wanted to show that now we're able to separate and be able to, for every single field, be able to know where these zones are. So these are zoom in. If you see the shapes of the fields, those are random fields that we picked, and how big those low productivity areas are versus what is on the unstable hilltops, and how. So this is very important in projecting under climate change and increased climate variability, such that the unstable hilltop with greater rainfall, and what is the fate of getting a certain level of yield as well as environmental outcome. So towards the end, we have a real possibility now to be able to convert areas that will lead towards climate benefits by applying the right amount of fertilizer, and scalable for basically the initial approach in this way, because so far precision agriculture has shown great potentials at each single field, but the procedure has never been really integrated to be scaled up. And so you can say that the map are easy to read. You can say the first one above, it's like, let's put the amount of fertilizer based on the uptake or based on what the plant is responding. And so the areas that they're low, they will get 50 kgs. The one below, it's if they were to be moved into a precision conservation, that corn was not even planted. And so you can see the benefits in CO2 equivalent if you were to move from the nitrogen saving. And again, this is scalable for the fields. So this is the variable rate possibility of scaling. And again, continue to apply fertilizer on the low zones and the nitrogen saving up to 120 kgs, but in up to 300 kilograms of CO2 converted into potential credits is just a simple multiplication at $15 now. But if you were to do carbon, precision conservation and not put, the nitrogen all together, then you start seeing a little bit of the greater benefits from reducing greenhouse gas emissions up to 600 kilograms of CO2 equivalent per hectare. So to conclude, one of the work that from the initiative that Jim Jones and I and other colleagues have worked, and actually part of this work was also John Hertl, who it allowed us to really bring the economic perspective that nothing really probably would happen on a short term unless it's incentivized or unless it's shown that these changes will lead to not at least a loss of profit. And so this is a linear system where there is, leakages, there is very little energy generated on the farms. Fertilizers are applied uniform, high input or low yielding areas, poor soil health, excessive amount of agrochemicals, drainage completely lost, genotype conventional with low adaptability. And so you name it. And versus what a potential, benefit could be by in depending on the technology readiness. So the ones, the boxes in white is, the possibility of using smart drainage system and re-irrigate using, again, native vegetation or bioenergy on low productivity areas, energy produced on the farm, bring the animal back into circulation for grazing system on some of the unproductive land, and so on. So this is all described in these two papers that we published. And so again, how we make this system a little bit more circular, it is possible, and actually all the way to reducing emission by 70%. If you go all the way to 30 years where we envision electrification of the overboard system or microbial-based fertilizer and biodigester. And so the food and fuel dichotomy is false. Energy can be produced on the farm, regenerated, become circular, as long you account for the system interactions and feedback. So with that, I just stop. And obviously this work wouldn't be possible without the work of these hard and passionate students and staff, and the funding agency that supports my lab. Thank you very much indeed.
Thanks, Bruno. We'll move on to our third speaker in the interest of time. Our third speaker today is Dr. Charles Rice. He's a distinguished professor of soil microbiology at Kansas State University. Dr. Rice is a co-winner of the 2007 Nobel Peace Prize for his work with the United Nations IPCC. His research focuses on soil quality measurements, carbon cycling, and climate change mitigation. He now serves on the National Academy's Board on Agriculture and the U.S. Department of Agriculture's Agriculture Air Quality Task Force. His presentation title is Transforming the Linear Agricultural and Food System to a Circular Bioeconomy. Chuck?
Hey, thanks, Madhu. So go ahead. I'm going to take a different approach, or well, back off. Bruno gave an excellent example of managing the landscape on the field level. So I'm going to take a little bit global approach. And if you go to the next slide. So we're going to be looking at transforming the linear food system to circular bioeconomy. Next. Yeah, thanks. So as Madhu mentioned in the introduction, we have a lot of challenges facing us, and it's, she mentioned climate change, but we also have degrading natural resources. Jim also mentioned this. Our soils are under extreme degradation. Just carbon alone, we've lost 30 to 70% of our carbon in our soils and becoming unproductive. Water, huge water problems, and that doesn't come up. Well, it comes up in many places, but it's critical in major food production areas, the central part of the Great Plains, in the Mideast, but other parts of the world, the scarcity of water, and that's exacerbated by the climate change issue. Ag productivity, these are zones here of, we often talk about natural ecosystems. We need to protect natural ecosystems. But there's our agriculture soils or productivity zones are under threat as well, not only from water and soil degradation, but from urban encroachment. And maybe we should be protecting our agriculture systems, or these critical zones that feed the world in our most productive climate and soil economy. And then the issue of encroachment of agriculture and biodiversity. All these are putting pressure on our ag food system, as well as increasing world population. So several years ago, you should all know the UN Sustainability Development Goals. And if you look at food and ag and the natural resources associated with that, we're looking at 2/3 of these directly affect the Sustainability Development Goals. Now, the obvious ones are food security, but the poverty greatly is influenced by the productivity of the food ag systems, climate change, and I can go on. But what Jim mentioned is I do chair the National Academy Board on Ag, and we've been dealing with some of these issues. These book covers are some of the things that we've been working on the last several years, developing a framework for food system, mitigating emissions, looking at using AI and other information to develop a more dynamic soil information system that Bruno chaired. And just basically, what's the research agenda for the next several years for food and ag systems. So with that, next slide. So we got all these pressures, and so really what we're talking, instead of boxing these into discrete boxes, we need to be thinking more holistically. And Bruno gave an excellent example. Of course, I'm a soil scientist, so I put soil security right in the middle. But the point here is that they're all interlinked. Depends on your point of view. You know, food is absolutely critical. Water, I mentioned that. Ecosystem services, climate change, they're absolutely critical. And they're all under threats. And we need to be thinking about these interrelationships and the connectivity, and also to meet the UN Sustainability Development Goals. Next slide. So Jim kind of presented a little bit of this, the MacArthur Foundation report. But right now, and particularly in food and ag systems, we're in a linear economy. We put on water, we put on nutrients, we put in energy into our ag and food systems. We produce a crop, we move it off to the farm, and it gets used by society globally. And Jim mentioned about scale. That's still one of the questions I have. But then, you know, where that food and all the exports of that energy and nutrients are moved off-site from the production for miles to even, you know, hundreds of millions of miles away. In a reuse economy, well, we think, okay, we're going to reuse some things, but we still have the input of raw materials into the landscape if we're looking at food ag systems. And then eventually they're reused, but then their recyclable waste accumulates in landfills. What we're looking at is trying to transform that linear system to a circular economy, and that's not easy. So Jim laid out the principles, and I won't reiterate them, but try to regenerate some of our natural systems, our natural resources, as much as we can. Next slide. So I pulled this slide from the publication here, and it's really thinking cycles of cycles, and also then at what scale. So, you know, we're looking at the carbon cycle. I put here the nitrogen cycle, but you can pick phosphorus or some other nutrient, the water cycle, and then the lower right-hand corner is the energy. So can we look at transforming our food ag systems to a circular bioeconomy? And the term circular economy has been used, but it's also somewhat extractive. And at least some of the folks that we've been talking to within the National Academy Board likes the bioeconomy, because now can we use agriculture systems, natural resources in a circular way to produce some of the products that we've been extracting with fossil fuels. Plastics, can we use more of that produced and recycled in that way? So we're looking at these cycles. Bruno mentioned about, using nitrogen fixation on the landscape legumes and maybe electrification of the Haber-Bosch process to fix nitrogen on the farm. We had a discussion this morning with a group, can we use, there's a lot of interest in energy production on farm, renewable energy, wind turbines, solar energy. Can we produce food under those solar panels, provide shading, and provide on-farm energy, and then export that energy in a renewable way instead of using extractive processing with fossil fuels? And so we need to circularize and look at these cycles at different scales. So next slide. And then, so if we do that, again, this is a copied slide here, but basically, if we can look at the circular bioeconomy, now we can realign the sustainability development goals in the sense of providing ecosystem services, providing food, biomass, and then the bioproducts that are more sustainable and less extractive in the sense of non-renewable resources. Next slide. So, but this is hard. It's going to be hard. We got to develop a whole cadre of scientists, engineers, policymakers. We need to be training our students to think in a systematic approach to advance innovation and entrepreneurship. So again, we've been linear thinkers, linear in our education, and we need to really develop that systematic and circular approach. We got to quit thinking of agriculture as just production of commodities. It's a production of resources that can be recycled and made circular. And again, the energy, and look at those nutrient biogeochemical cycles, the energy cycle. What is also going to take, and we've discussed in the on Banner, is we're going to do a study on food and ag systems. We're going to have to involve all sectors, not just the agriculture industry. I forgot who mentioned it, but we need to be thinking, if we move off the farm gate that Bruno was talking about, now we got to start talking to the Walmarts, the Amazons of the world, because they are going to provide the incentives, the pressure, economic pressures to instill some of this, the bioeconomy, the circular bioeconomy. We're going to have to engage those individuals, those groups into the discussion. We can't do it just alone within a narrow confine of agriculture production. And as we scale up from, the farm gate to statewide or national and then global, it's definitely going to have to involve those individuals. So it does have to be transdisciplinary. I don't think anybody's mentioned, but maybe Bruno mentioned a little bit. We need to involve the economists, but my gosh, we got all these technologies. We're going to have to include social scientists into the adoption. And that's one of our barriers. We have technology tools right now, Bruno's favorite AI tools, but there's sociological barriers there in order to adoption, and particularly as we scale up, it's going to take a lot more social skills as well as the computer science skills. And so with that, it's going to be quite a challenge. I think it's an exciting time for agriculture, but it's going to take some effort and innovative thinking on this. So with that, I think next slide is just my ending slide. Yeah. So thank you.
Thanks, Chuck. We'll move to our final speaker today, which is Dr. David Zilberman. He's a Robinson Chair and the Professor of Agriculture and Resource Economics at the University of California at Berkeley. Dr. Zilberman is the recipient of the 2019 Wolf Prize in Agriculture and a member of the National Academy of Sciences. His research is on the economics of agricultural technology adoption, innovation, and supply chains. And he's going to be talking today about sustainable development and the circular food system. David?
Can you move can you move to the next slide? I can speak directly without slide to be much faster. Okay, so what happened is that we are facing a lot of challenges. We have to feed 3 more billion people, control climate change, develop alternative sources of energy, and I think that agriculture can be a key for all of it. Now, there are a lot of concepts that everyone has imagining: circular economy, the bioeconomy, regenerative agriculture, agroecology, precision farming. There is all this soup of terms, and people really don't know what to do with it. I was in the UN World Food Summit task force, and that was the debate. Where are we going? So my starting point is sustainable development, which is a more general concept. And from there, I'll try to look at all these other concepts and argue what the role of sustainability. To me, sustainable development is really crucial. It's a concept to move forward while staying at the same time. But that's what science is doing. Science is trying to bridge in conflict. And sustainable development, it's not a slogan, it's really this is our challenge of our time, growing without destroying. And the way to look at this, and it has multiple dimensions. It has a dimension of economic, it has a dimension of sociology, and it has a dimension of the environment. Now, the starting point for sustainable development is the definition of the Brundtland Commission that sees sustainable development is a development that meets the needs of the present without compromising the ability of future generations, which basically assumes that humans are the most privileged species. It's anthropocentric, and looks at the interest of further generation. From an economist perspective, it basically adds interesting extra dimension of a constraint. You cannot maximize growth over time, but you have to take into account that minimum income is not declining, and that you basically have to leave resources to other groups. And over time, it really suggests increasing the notion of the way we look at economic growth, to consider human capital, our knowledge, a physical capital, our machinery, natural capital, our environment, and social capital, our system, and we preserve and let them grow together. Now, so there are a lot of models that can introduce a sustainable development, and the notion of sustainable development really requires multidisciplinarity. I think this is the key that I see, incorporating economic and social and biophysical model together, to work together to develop a decision-making that are multidisciplinary and are incorporating things. Now, I think that for me, economic is very important because economic is basically an integrative discipline. We try to look at different perspectives of the environmentalist, of the farmer, of the consumer, and bring them together within the policy making so we can have outcomes that will work. Because when I speak with scientists, I hear all these wonderful technologies, but my question, will it be adopted? And my personal talent always is trying to develop supply chain and marketing plans that would make technologies adoption. But in the side, from the past, there are several lessons that we have to use before we go forward. The first lesson is the important reliance of science. We need to have science-based agriculture, and one of the biggest challenges is to sell science to the community, because you see what happened with the vaccination. The other thing we have to take into account side effects. We have to look at pollution. We have to look at climate change. We cannot have production for production's sake, and therefore there is the role for the state. Now, the state and the system that we have that works best is mixing the private sector with mixing market forces with enlightened active government. People always speak about the greatness of the private sector of America. But to me, I think the greatness of America is a combination of private and public sector, the educational industrial complex, the land grant system, together with market activities and regulations that basically preserve the environment, and that is the challenge that we are having today. So if we look at how we can attain sustainable development, there are 5 types of strategies. First, conservation, basically to reduce the conserved use of non-renewable input, but without reducing output. This is a big, big challenge, basically, and I'll speak a little bit more about it, and this is where circularity enters, to use less resources to produce more output. The second thing is to move away from non-renewable. The third thing is recycling, so we can use mineral, and then use renewable resources, and then I'll speak a little bit about what I care a lot about is the bioeconomy. And first thing, we cannot avoid circularity. Conservation of mass is the physical law, you cannot ignore it. So linear systems that start with input and end with output and ignore mass balance, and this is where a lot of our systems are against nature and basically generate a lot of problems. We need to introduce circularity and develop technologies that increase input use efficiency, namely the amount of input that directly used by the crop. Input that is not used by the crop, that is not used by the system, generally end up as a waste or as a pollution. So increasing input use efficiency by precision farming, by drip irrigation, by biotechnology, by any means to increase input use efficiency is crucial. Let's see what happened in electronics. So challenge number 1 is increasing input use efficiency that will contribute to circularity. And conservation technologies are very important. The second thing is precision farming. To me, precision farming is above input use efficiency because you take advantage of information technology and apply input better. Now, I have a approach for precision technologies that it basically has 3 elements: monitoring, assessment, and application. Monitoring can happen with remote sensing. Assessment requires a lot of modeling, and we only in the beginning. Believe me, I'm an economist that work on this stuff, and our models are not that great. They can be much, much better with artificial intelligence and other things. And then the toughest thing is application, to develop systems that can apply precision technology. And now with yield monitors and other things, we are moving forward, but in the future it will be better. So we need to develop technologies that will basically monitor better, model better, and apply better, and automatically they will reduce pollution and reduce losses. Another thing is the transition to renewable, and then we can speak about solar and wind and all this stuff, and they can be on the farm. But the big thing is basically using living system, using basically moving from a system of harvesting to system of basically of breeding, feeding, so basically to farming. And the transition to farming is not only crop, the transition to farming include also a transition to aquaculture and a transition to produce a lot of chemicals through biology. So to me, the bigger challenge is the renewable economy, and the renewable economy by nature will be circular because we will try to use as much residues within our feedstock. And the key point in all this stuff, in my view, is the biotechnology, is the bioeconomy. And the bioeconomy basically means using all the capacity of biological systems that use biological knowledge and living system to produce a lot of outcomes. There is a traditional bioeconomy that rely on fermentation, and there is a new bioeconomy that use modern molecular biology. And to me, the biggest challenge of our generation is to incorporate molecular biology with soil science and agronomy. You cannot, we need to have one agriculture that take advantage of everything, because combining biotechnology with precision farming and advanced agronomy, that is the challenge of our time. Because to me, we cannot deal with climate change without, and other challenges, without looking at agriculture not as a source of food, but as a source of chemicals, as a source of fuel, and a source of a lot of other products. And if you look at it, we basically utilize about 20% of the resources in our food. We can increase the productivity of photosynthesis. So we really need to move to a system that we basically sell to the world that you need to have a regulatory system that agriculture is challenged with trying to solve climate change by developing new mechanisms for sequestration, increase productivity, and providing alternative sources of food and energy. So to me, the circular economy is a key element, because we try to reduce waste and keep ourselves within the notion of a mass balance. But within this perspective, agriculture now become a key element to produce raw input, not only for food, but for energy and for chemistry. And I'm sure that we are up to the challenge. It's an issue that we need to have new technologies, but we need to fight very much for new regulations that will allow agriculture to meet its potential. Thank you.
Thanks, David. All right, we've just got 2 minutes. So as a closing, I'm going to ask for each of our speakers to give a 30-second thought on, what is the sort of most important research question that should be addressed? What is the sort of important research area in order to move towards a more circular economy? So maybe start with Jim.
That's a really tough question, Madhu. There's so many things to do, just like Chuck said. I mean, it's a real challenge. It's really complicated. Our systems are complex, and they sometimes create unexpected outcomes and vulnerabilities that we have to deal with. But I think there needs to be opportunities for people to look across disciplines and try to connect these things that we're doing in the production and supply chain side, along with the types of skills that I think David was talking about and John Hertl is working with, and Tom Hertl as well in the economics. We need to have good examples of that. I'm pleased with some of the work that Bruno has recently done that shows good examples already of some of the things and the vision for making changes in the future. And I also, by the way, really like the use of the circular bioeconomy that Chuck suggested and David mentioned also. So we need to rally around and work together on this because it's so complicated.
Thanks. Bruno?
I would say that, there were even questions in the chat about, the barriers. And I think we are far from understanding trade-offs. If we do, we don't have the coupled system together. I mean, I have the privilege to work with economists, and when we use models, the example of, be able to quantify leaching or, best management strategy, it's, I guess we could say it's easier to identify, but if it doesn't pay the bills or if it doesn't get adopted, it doesn't go anywhere. And so the possibility, to me, the biggest hurdle is to understand, how low can you go? What is basically the low-hanging fruit of bringing these two teams together such that a management decision is supported by a full economic analysis that could show policymakers a reduced risk in implementing, because as being thought not from just the environmental perspective, but also from the economics, because if it doesn't get adopted, it doesn't do any good. So trade-offs and system approach are the two key words for me to implement circular economy.
Thanks. Chuck?
Yeah, good question. It's really complex. And when the Banner study I've told people it's probably going to have to be a 2 or 3 year study because it's so complex and you have to involve so many different folks. I think one of the challenges I always asked Jim was the question of scale. Where do we stop? Farm gate, we talk about, national or international. As it gets bigger, it gets harder. Somebody asked the question about, smallholder farmers. Actually, if we start putting value on waste, returning, human waste or, those nutrients exported back onto the farm, it makes those smallholder farmers actually of greater value because of the local nature and that. But I also would argue that you do have to include some of these companies because consumers are going to put pressure on the companies, but the companies are going to be, the Amazons or the Walmarts are going to be the ones that's going to implement the system, at least the way our economy is right now in the developed world. They are going to, Walmart's already talking about sustainability and that some of their goals are maybe not appropriate, but they're going to be the ones that interface between the consumer and the producer. And so you have to include them in our current economic system.
David?
We need to integrate technology and policy within supply chain. I think that is a big challenge. I think also we need to have much more dialogue. Like when I hear Chuck speak or Bruno, and I start to look at the stuff that we are doing, we have a lot of knowledge in social science that people in ag don't have. For me, it's obvious that you have to go below the farm gate. It's obvious that you have to think about how innovation are working. To me, work within agriculture is very limited. To look at the issues of the bioeconomy that is going beyond agriculture is very, very important. But we need to have some sort of dialogue so people can speak in a similar language. And the other thing that I really think is very important, and within US university, that people that work in plant breeding and people that work in agriculture work together, because today we have a really divided agriculture. And when I look at the World Food Summit, what I hear is that the pressure is to move to something that's called agroecology. I don't know if you believe in it or not, but I worry about it. But because the science-based agriculture doesn't speak in one language, we really have a situation that all these, what I call voodoo agronomists, come with the new ideas, and to some extent we really need to develop a coherent system where technology, policy, all integrated within supply chain, and we work together with the private sector rather than we basically work as if we are separate. Thanks.
Thanks, David. Okay, well, I think we will conclude with that. So I'd like to thank our 4 panelists for such thoughtful talks, and it's been a pleasure to hear from all of you. I would like to also thank CFAIR, the Economic Research Service, and the National Agricultural Statistical Service for supporting this webinar series. And thank you all for attending the seminar today. There is information about the next seminar that is going to come up on November 3rd. That's going to look at how we reduce waste from the agriculture and food systems. So please sign up for that. And with that, we'll close our series for today. So thank you all for attending.